So this, if this is 1, 0 spot, this is my center 2 by 2 spot. It really is 1/2 the spacing of the original substrate spot. Okay, so everybody get that? So my point is this. My point is that you see weak spot, but on the bright spot, you also have weak spot as well. It's just that you don't see the weak spot on top of the bright spot. So you must consider the existing bright spot, which is the substrate location, when you calculate the length of the residual space. Okay, so that's one thing. So you can see right away that when I have twice the distance, right, I really just have half of my original, right, because this is my center 2 by 2. So the residual space should be 1/2. The length should be 1/2, as we try to calculate down here. All right. So that's a bit of a fine point. And now, if you look at another pattern, let's say, so here I can see it very okay. So here, if you look at this pattern, right, what do you see? You have the open circle. That's my 1 by 1 spot, right? That's my substrate spot. And now you have for the atom, for the absorbed atom, you have 2 units, isn't it? Right? So what do you call this? You call this 2 by 1, right? The other one. So the open circle is my 1 by 1 original substrate. The absorbed or the overlayer, because you have 2 distance here, will be 2 by 1. And where do you expect the diffraction spot? Well, if you look at it this way, so you have this is my original, right? The square is the bright spot, represented by black dot, is my original. And then the fractional spot you see, right? Because this is 2 here, you should have a fractional spot in between, right? So that's additional spot. So you have spot here, spot here, spot here, all weak spot. And you don't see the weak spot because there's already right spot overlapping the weak spot. So that gives you this vector 2 in residual space, because it's 1/2, right? So you have 1/2 for this fractional spot. Now in this direction, you have 1 by 1 because you have 2 by 1. This keep the same distance. So then the weak spot should overlap your bright spot like this. Okay. So what you see is that you see these guys are bright. The one in blue is weak spot, and that will be what you see in the leak pattern, in the diffraction pattern. Okay, so it's a little bit you have to be a little bit get used to this thing to imagine what you see, because you have this overlapping 2 patterns, one coming from the substrate and the other coming from the overlay, and of course the bright substrate pattern will overlap your substrate pattern at a certain location, at a certain point where the substrate, and you would not see the weaker overlay spot because of that. And so you have to be careful when you are looking at these spots that you see. All right. So what is the diffraction condition when you are? So this is just straightforward pattern recognition that I'm trying to illustrate. You can go from view space to residual space using this sort of transformation system that we have. Now, what is the diffraction condition? Diffraction condition is, again, I use a similar way as in X-ray diffraction, is that you start with elastic scattering. So the electron beam is elastically scattered. That means the kinetic energy does not change before and after the collision. So when you write kinetic energy, you can write it in a different way, right? Instead of 1/2 mv squared that we are familiar, you can write it in terms of momentum. So if you put it, so you can write kinetic energy p squared divided by 2m. So kinetic energy is proportional to p squared, right? And if you write p to be Planck's constants times this so-called momentum or wave vector that you got, then you can think of this just momentum, right, squared. So let me write it like this. So E, what I'm trying to do, E is really just p squared divided by 2m, right? And really P, if I write P is equal to hk, this is how physicists write this, it's a constant, this is a wave vector of the direction where the particle is going. So you really just have x squared 2m k squared. So this is just a constant, so kinetic energy really just proportional to k squared. And that's what I have. And these are universal constants, so if I consider E incident equal to E scatter, then this will cancel out. What I end up is just a momentum vector square equal to one another like this. So this is an incident, this is the diffracted beam like this, the scatter beam like this. Alright, and so you can expand this. Of course, this is a vector, so you can write this vector square as what? As kx squared plus ky squared plus kez squared in 3 dimensions, and you call this one k parallel squared plus k perpendicular squared like this. Right? So it's just an expansion like this. So really when you write kinetic energy, the definition of elastic scattering, you can expand it into like this, and you expand it into parallel, meaning surface parallel, and then perpendicular, meaning perpendicular to the surface plane, this way. And so in the case of surfaces, you're only concerned about parallel, conserving the parallel component, because the perpendicular component you don't see, because that's kind of give you the change in the kinetic energy. So the conservation condition is that the parallel beam, right, should be parallel k on the surface, right? This parallel means on the surface. Should be the incoming should be equal to the outgoing plus a residual lattice. The reason why you have plus residual lattice is that because of the translational symmetry of the surface, because you have periodicity in the 2D dimension. So you move a residual lattice, you have no way of knowing whether you have moved or not. That's really just, it's the same as what we are talking about in 3D X-ray diffraction, whereby you're talking about just K plus K incoming equal to K outgoing plus a big G, where G here is a 3D, right, X, K, and L residual space vector. And this is just a residual net vector on the 2D surface. So it's a completely parallel. So I say GHK is the residual vector of this surface net. So this is how you would get conservation of this. Really just due to translational symmetry of the surface that you got. And the perpendicular component is not conserved. They just go into, the electron just, part of the energy just go into the surface, if you like, the perpendicular direction goes. Okay, so how do you generate your diffracted beam? It's very easy. There's something called the Ewald construction, spear construction. I just show you this briefly in case that you come across it in future. Most people don't do that, but then in case you talk to physicists, you can generate, if you like, you can generate where you expect to see diffracted beam kind of thing. And this is one recipe, if you like, of how to identify the diffracted beam. So look at 3D case, which is the XRD case, right? When you do X-ray diffraction that you have. So what do? You draw your 3D vector, right, from the origin of your visible space, and then you basically from this. So let me give you a picture of this. So imagine that I have this grid. This dot represents a reciprocal space point, not a real space point now, right? So we have to think in reciprocal space or momentum space, think of it like that. And this point, right, this point has, I'm just taking one layer of this point, right? So imagine now that I have